Welcome to Maths with EJD. In this video, I'm talking about paired t-tests, and this will be the last I'll be considering under parametric test. After this, I'll be taking the non-parametric tests one after the other. So let's go on as we discuss paired t-test. So the paired t-test is a statistical method to determine whether the means of two related groups are different from each other. This test is commonly employed when measurements are taken from same subjects at two different times. At two different times or under two different conditions. So if you're wondering how a pair t-test is different from a two sample test, for two sample test, you're actually testing for the whether the means of two independent groups are equal or not, are significantly different or not. But in the case of pair t-test, you're looking at whether the means taken from the same group at different times or under different conditions, whether they're significantly different or not. So that's a test, paired t-test. Okay, so here's okay, I mean, we are here to talk about all the nuances of a paired t-test. So let's do that. Well, the first thing is to understand the paired t-test, right? Which I've given a kind of background on that. So let's talk about understanding the paired t-test. Okay. So first of all, when to use a paired t-test, first you have two sets of related data for two sample t-tests. You have two sets of unrelated data. That's the key difference. Then here the data are normally distributed. Okay, and the third point is that the measurements are taken from the same subjects, making them dependent samples. Okay. Two sample tests, independent samples, paired t-test, dependent samples, basically. So we go for formulation. So the steps now, formulation of hypothesis. Two hypotheses now. So you have the first one, the null hypothesis, what you call H naught, and it says that there is no difference, or there is no significant difference, if you like. There's no difference in the means. There's no difference in the means of the two measurements. Okay. Mathematically, this can be stated as H naught, that's mu d, equals 0. That is the difference between the values are not different. Here now, mu d, mu d is the mu d is the mean difference, mean difference between the paired samples. Mean difference between the paired samples. So that's the null hypothesis. Two, you have the alternative hypothesis. Alternative hypothesis, which you can call H1 or HA as you may choose. So let's call it HA in this case. HA. So HA will just be the negation of the H naught. So there is a significant difference. There is a significant difference between the means. Okay, this can be two-tailed such that HA would be that mu d is not equal to 0, meaning that there's a significant difference. Then, or it can be one-tailed. It can be one-tailed such that HA is given, HA is mu d is greater than 0, or HA is such that mu d is less than 0. So when you incorporate, when you talk about greater than or less than, that becomes one-tailed. But if it is just simply equal to 0, I mean not equal to 0, then that is two-tailed. So the next thing is to talk about steps to conduct a paired t-test. Okay, first thing, you collect data, which you would mostly already have. Like if you're in an exam situation, you are presented the set of data. So you have to obtain two sets of paired data. So the fact that it is paired arises from the reality that it is data taken from the same sample. So obtain two sets of paired data. That is, take measurements from the same group at different time points or under different conditions. For instance, you may want to check, a good example would be maybe you have a set of 50 students and they wrote they wrote a math test and then they wrote a physics test. So if you take those two scores now of the same group of people, so a very good test for that would be paired t-test, because it is data you collected from the same group under different conditions. So two would be to calculate the differences. You need to calculate the pairwise differences, if I can say that. So say for each pair, compute compute the difference. Compute the difference, which you can call d sub I. So d sub I is equal to x2I minus x1I. That simply says, the corresponding values, maybe math score, physics score, the corresponding scores is subtract. Okay, so here, where x2I is the second measurement, x2I is the second measurement, and x1I is the first measurement. So the second comes before the first. Okay. Yeah. So then we talk about 3. Okay, I guess I can still continue with this. 3, you calculate, yeah, you calculate the mean and standard deviation of the differences. So it's not of the actual numbers now, it is of the differences. Okay. So the deviation of the differences, for instance, deviation of the differences. First, talk about the mean. Talk about mean. Oh, okay. What am I doing? So we've already talked about calculate the mean and standard deviation of the differences. So first of all, you talk about the mean of the differences. Mean of the differences is such that mean of D equals summation of DI divided by N. Okay. And then next we have the standard deviation. Standard deviation of the differences. So this is exactly the kind of thing you do for the uh for the paired Z test. For the paired Z test, the only difference there is that you're talking about a population whose variance and standard whose variance is known. And of course, if you know the variance, just take the square root and you know the standard deviation. Or for a population with that is not that large sample size, yeah. For a population that has for a sample size that is large, that's just the difference, but it's exactly the same kind of approach. So standard deviation of the differences is the next thing you need, and that is simply ST equals, as usual, summation of DI minus D bar all squared divided by N minus 1. Because for t-test, normally you're talking about sample size less than 30. That's N less than 30. Okay. Then we go for 4, which is to calculate the t-statistic. Calculate the t-statistic. In this case, the t-statistic is calculated as t equals d bar divided by st divided by square root of n, like that. So here, where n is the number of pairs, is the number of pairs. Of course, before now, you already came across the standard deviation SD. So it's the standard deviation. This is the mean of the difference. This is the number of pairs that you are working with. Then we talk about number 5. Number 5 is to determine the degrees of freedom. Degrees of freedom. That is DF. So in that case, that's just df equals n minus 1. Of course, n here is the number of pairs, not the individual, measurements. It is the number of pairs, simply, that just like the n up there. Then we go for 6, which is to find the critical value. This is from where you get the critical t value. So find the critical value. So here, use a t distribution table. Use a t distribution table to find the critical value for a given significance level. So you have to choose the significance level you want, or if you're given, you follow that. So for a given significance level, so the smaller the significance level, the stricter your test, so to speak. So commonly you use alpha is 0.05. That means you want five, you are allowed 5% chance for error. If it is 0.0, you're only allowed 1% chance of error. So, and of course, you have to base that on the degrees of freedom, which you had earlier found in step 5, the degrees of freedom. Okay. And lastly, you have to make a decision. Make a decision. So make a decision. The decision rules will be this. If the absolute value of t is greater than the critical value. So anything you calculate normally should be less. If you take the absolute value of both sides, anything you calculate should be less than the critical value you got from you will get from the table for you to accept the null hypothesis. But if it is greater, like in this case, what you do is you reject the null hypothesis. You reject the null hypothesis. Otherwise, if the absolute value of the test statistic you calculated is less than or equal to the critical t value you get from the table, then you fail to reject. That's another way of saying accept, right? You fail to reject the null hypothesis H naught, right? You fail to reject the null hypothesis H naught, like that. So let's take an example to drive the point all the way home. So, example, a researcher, a researcher wants to determine if a new study technique improves test scores. Then 10 students, of course, don't forget, for t-test, you need sample size less than 30. So 10 students is a good one. So 10 students take a test before and after using the technique. Yielding the following scores. Okay, so you have like student, the score before, which we'll call x1. Then you have after, which you can call x2. Okay, so student 1 before 78, after 85. Student 2 before is 82, after is 80. Student 3 before 76, after 90. Okay. Student 4, 88, 91. Student 5, you have 79, 84. Student 6, 85, 88. Student 7, 90, 95. Student 8, Student 8, 70, 73. Student 9, 77, 80. And student 10, you have 81, 87. Okay, so because naturally the next thing we want to calculate would be the difference, right? So let me just, instead of making another table, I'll just say difference, which is D now. Of course, basically that is x2 minus x1, like we know already, x2 minus x1. So since it's x2 minus x1, right, that's 85 minus 78. That is 7. Then 80 minus 82, that's minus 2. 90 minus 76 is 14. 91 minus 88 is 3. 84 minus 79 is 5. 88 minus 85 is 3. Then 84 minus 84 minus 79 is 5, yeah. Then 6. 88 minus 85 is 3. 95 minus 90, that's 5. Then 73 minus 70, another 3. 95 minus 70 minus 73 is 3, right? Then 80 minus 77, another 3. 87 minus 81, that is 6. So those are the differences. So next thing we need to calculate, okay, we've calculated the differences already. The differences are 7 minus 2, 14, 3, 5, 3, 5, 3, 3, 6. Okay, so the next thing we want to do is to find the mean of differences. Mean of differences, okay, is such that d bar is equal to 7 minus 2 plus 14 plus 3 plus 5 plus 3 plus 5 plus 3 plus 3 plus 6 finally, divided by 10, I believe. Yeah, so 7 minus 2 is 5 plus 14, 19 plus 3, 22 plus 5, 27 plus 3, 30 plus 5, 35 plus 3, 38 plus 3, 41 plus 6, 47. Have I done something wrong? 7 minus 2 is 5, 19, 22, 27, 30, 35, 38, 41 plus 6. That should be 47, right? Let's see. Minus, I mean, that's 5, 19, 22 plus 7, that's 27 plus 3, 30, 35, 38, 41, 47. Yeah, 47. So D bar is equal to 47 divided by 10, which is 4.7. Okay, so D bar is 4.7. Then we go ahead to talk about the standard deviation. Standard deviation of differences. Okay, let me start color coding again here. This is 4.7. So standard deviation of differences. So I think doing it in a table format is always the best. Like I keep saying, so you have, cos D bar is 4.7. So if you want to do the difference, I mean, the, of course, okay, first of all, we know SD is square root of summation of di's minus d bar all squared divided by n minus 1. So we need di minus d bar. That's the big work. So we already have, we know our di, right? That will be 7 minus 2, 14, 3, 5, 3, 5, 3, 3, and 6. Okay, those are your DIs. Then we have DI minus D bar. Don't forget D bar is 4.7. Okay, so we have all this. Okay, let me go through all the pain here. So this is of course we also need DI minus D bar all squared. So let's do it step by step here. I mean, this is standard practice. I've not done this so far. I just kept jumping when I think I want to commit a bit of time to this. So DI minus D bar. So this is 7 minus 4.7. Okay. And next we have minus 2 minus 4.7. Next you have 14 minus 4.7. Then you have 3 minus 4.7. Then you have 5 minus 4.7. Again, 3 minus 4.7. Then 5 minus 4.7. And 3 minus 4.7. 3 minus 4.7. Again, 3 minus 4.7. And lastly, 6 minus 4.7. So we're going to have to square this after it's all done. So let's do that. So let's go 7 minus 4.7. 7 minus 4.7. Okay. Okay. 7 minus 4.7. All that squared. So that will give us 5.29. 5.29. Then what about minus 2 minus 4.7? Minus 2 minus 4.7. That is 44.89. When we square that, then 14 minus 4.7. 14 minus 4.7 all squared. That is 86.49. Then 3 minus 4.7. 3 minus 4.7. 2.89. So, and we have quite a number of threes. So this is also 2.89. This is 2.89. This is 2.89. Okay. 5 minus 4.7 all squared now. 5 minus 4.7 all squared. That is, okay, of course, 5 minus 4.7 is 0.3. So 0.3 squared is 0.09. So this is also 0.09. Then we have just 6 left. So 6 minus 4.7 should be 1.3. So we get 1.69 or so. 1.69 for sure. So we need the summation. We need summation of all DI minus D bar all squared. So let's do that addition. So we have 5.29 plus 44.89 plus 86.49 plus 2.89 plus 0.09 plus 2.89 again plus 0.09 again plus 2.89 plus another 0.09. Okay, 5.29, 44.89, 6.49, 2.89, 0.09, 2.89, 0.09, 2.89, another 2.89. We need to be really careful. And lastly, 1.69, 1.69. So that gives us 150.1, 150.10 if you like. Of course, now the standard deviation, again, I think I don't mind repeating that square root of summation of all di minus d bar all squared divided by n minus 1. So, of course, we have 10 pairs, right? This is 1, 2, 3, 4, 5. Okay, I mean, that's not necessary. The question already told us we have 10 pairs, so let's not waste time with that. So n is 10, as we know already. So this is square root of 150.10 divided by 10 minus 1. So SD is square root of 150.10 divided by 9. So 150 now divided by 9 is equal to, so SD now is equal to square root of 16.6778. Okay, so square root of this now, so square root. So if you're working with statistics like this, you need to get a calculator that you have mastered. Avoid the error of getting someone else's calculator on your way to the exam hall. You can be disappointed because calculators differ. So you need to use something you have always used while practicing. So you don't have to try to, I mean, you don't want to start figuring out how to use someone else's calculator in the exam hall or on that, so a situation where you're being examined. 4.0838. So that's deviation, the standard deviation here. Okay. So we have that now. And then the next thing, now that we have got the standard deviation, is to go for the test statistic. So we have found the standard deviation of differences. So next thing, let's talk about the test statistic. So calculate the t-statistic, and of course the t-statistic is computed from t equals d bar, the mean of that, divided by SD divided by square root of n. So d bar, from what we already got, was 4.7. Yeah, d bar is 4.7. That's the average of the differences. That's 4.7 divided by our SD now is 4.0838 divided by square root of 10. So it means that t is equal to 4.7 divided by 4.0838. And so I mean, approximation begins now. So square root of 10 is 3 point something. Let's see what exactly that is. Square root of 10. Square root of 10. Square root of 10. Square root of 10. So that is 3.1623. Okay. So t is approximately 4.7 divided by 4.0838 divided by 3.1623. That is 1.2914. So t is approximately 4.7 divided 4.7 divided by 1.2914, and that is approximately 3.6395. That is our test. That's our test statistic. Okay, so the next thing is to get the degree of freedom, I think. Yeah. So next we need the degrees of freedom. Degrees of freedom. So that's df, which is n minus 1, and that is 10 minus 1, and that's simply 9. So that's easy peasy. Then we go for the critical value, which will involve the degree of freedom. Critical value. So, we've always assumed a two-tailed test. So we say for a two-tailed test with, the two-tailed test just generally assumes that the mu1, I mean, the difference in this course is not equal to 0. We don't care whether it's less than 0 or greater than, but it's just not equal. So for a two-tailed test with alpha equals 0.05 and df, degree of freedom, equals 9, the critical value from the t table so just like calculator, you don't want to borrow, so you don't want to collect someone's table on your way to the exam hall. Use a table you've always used for your practice. So by all means, so the critical value from the t table is approximately 2.262. So how do this compare? How does this compare with what we calculated already? So we go for 7, where you talk about the decision. So what kind of decision do you make with what you have already? So check the absolute value of t, the absolute value of the test statistic is 3.6395, or just that's 3.6395. Okay. Like that, or approximate. Yeah, let's leave it like this, 3.6395. And then your t critical that you got from the table, T critical is equal to 2.262, 2.262. And what happens here? Since the absolute value of T is equal to, I mean, it's obviously greater, right? It's greater than the T critical. Okay. It's greater than the T critical. So we have to reject. We reject the null hypothesis H naught. The null hypothesis H naught. So, and what do we conclude? What do we conclude? Yeah. So, based on the results, we conclude that the new study technique, has a statistically significant effect. Statistically significant effect on improving test scores. As evidenced by the rejection of the null hypothesis. Okay. Thus, we can confidently say that the average score after the technique is significantly higher than before its implementation. Okay. And this is exactly how new policies come by, especially for people who really care about empirical studies. So after this kind of research, you can now recommend this system for a school or for, I mean, you can also test it in other places. You can have pilot places where these kind of things are tested. And once that works, then it can be generally recommended. So with this, we come to the end of this video on paired t-test. You definitely don't want to miss this kind of thing because I have lots more for you. So you need to subscribe to keep in the loop and then hit the notification bell so you can always get notified each time a new video is released. Don't forget to comment. What are you going to comment about? You want me to teach a topic or solve a problem? Comment about that, or you like what I'm doing? Feel free to say that too. Then, of course, don't forget to like also and share with other people so that more people can have their confusions cleared. Have a nice time. See you next time. Bye.